Welcome everybody. We're back doing work on the Nexus mods app today. I was able to fix a couple of things we were dealing with yesterday, mostly around the data grid and stuff like that. But we're going to work on this deadlocking issue that we looked at. I did a change in MnemonicDB. We can actually probably take a look at that in a second. But we're going to start today by just updating that library in MnemonicDB itself, or sorry, in the app itself, and try to get back to, and I'm forgetting what the name of that pull request was, so let's find that. So here we are. So there's a new version of the database out, MnemonicDB. It turns out it was a deadlock between something pushing an update out of the database and someone else coming around and subscribing, and both were using locks, causing a kind of like a deadlock between the two of those. So we'll see if this fixes it. Hope it does. What I ended up doing was going into that subscription part of the database and making it lock free. So we'll go from version 8.4 to 8.6. Then we'll clean and rebuild this and see if we can get it to break again. I'm going to switch the scene here real quick as I clear out some folders on my system. We don't have data upgrading done quite yet on the app. That's coming soon. So until then, we have to kind of do this, you gotta clean out the data model when we do a big change like this. It sucks. I want to change that soon, but aren't quite there yet. Music today is a playlist from a set of like SoundCloud synthwave lists, and we'll give it a listen through. Got a whole bunch of synthwave tracks. I'm really into synthwave, so if you don't like that, sorry. Kind of got into synthwave waiting for Cyberpunk to be released, and never quite kicked the habit, so it's been many years of synthwave being the main music I listen to. Okay, so that builds. Let's make sure our tests all pass. And then we'll go in and download some collections again and try to get that whole thing to die like it did before. It is kind of fascinating to me that we're running these tests in parallel, and you can see them like they complete super fast. But if you look up at, or down, I guess, on your screen at BTOP, we're not really seeing that many, that much disk usage, or CPU usage, which is kind of weird. I would have expected to see more cores pegged, but, yeah, well. Okay, so tests are still running. Oh yeah, this collection test here takes a while. Is this the one that you said? We think that deadlocked before. Was that what we were? Well, that was UI based, so I don't know if that's the case. Some we can do is like rerun this. I was assuming it was a subscription inside MnemonicDB that had died, but that may not be the case. So we'll see here if that completed. We'll do it again here. That worked. I wonder if it's a race condition of the test. At any rate, we'll give this a try. So, yep. Log in. Authorize that. Add Cyberpunk. I think I still have this collection from yesterday pulled up over here. I do, in fact. So we look at the library, add the collection. That collection installed. By the way, that is like actually how fast collections install in this app. It's pretty wild. Okay, so that worked. What we did before then was like select all of these and delete the mods and try it again. That worked. These didn't show us installing. That's interesting. Oh, did they read? Oh, that's weird. Something may be up with the subscription on those. Let's delete them again. So that's... say that fixed the issue. This is another issue that we'll have to look at, but that may not be the case. We'll do it one more time, see if we can get it to break. We haven't been able to get it to break yet today, so that's always a good thing. Oh, that was even faster. Goodness. All right. Yes, that works. Update to the newest version of MnemonicDB so that we can fix the lock issue introduced in the previous versions. Cool. So we will put that up. And then over here, I'll go ahead and create that. Actually, we create the pull request in here, can't we? Oh, no, it's already a pull request. So we just got to not mark it as a draft. I'll put a note on this. It seems like the deadlock was fixed by making the subscription lock free. Cool. So we'll see what happens with that. The previous tests were failing. I think that was because that was a draft. Oh, hello, Trons. Good to see you here. Yeah, it's so the collections installing kind of happens in a couple phases in the new app. We have download, analysis, and install. Once we get the page built out that we're working on, I don't know if it's still here, the collection download view. Once this is fully built out, the first two phases of that download and analysis will happen as you're downloading the mods. And then when it actually comes time to click install, that's basically just metadata configuration. There's a couple things that have to be done there in some cases. Some mod types are a little more complex. But in general, it's wicked fast. Cool. So there were a couple of things I thought about doing in MnemonicDB that would be a good thing to do on a stream here. So I think we'll switch over to that. Oh, we're in the app. So I guess as a basic example of what MnemonicDB is, and like I said, I do want to do a tutorial eventually about some of this. So the database that we have is based off of this idea of a datum. And what a datum is essentially a tuple of an entity ID, an attribute, and a value. And then the last one is the transaction ID. And so you don't so much define a schema as you define the definition of an attribute. So in the case of a loadout, here, this is a test example of a loadout. We say, so we're going to define a loadout, and that loadout has an attribute called name, and the name is a string. This is going to be a fun one to explain. But here in the mods also have a name. So we have a mod has a name. In this case, it has a source that it came from. This is a demo model, so not a model that is actually in use anywhere. In fact, let me increase the size of this view a bit because it's a little small to see. But I don't know why that keeps switching back when I click it. Oh, you know what it was? Check this out. Okay, so I do appearance, zoom IDE, I go down to 200, it resizes the window. So when I click, it clicks the wrong thing. What a terrible design. I'm like in a race to click the thing with the UI resizing. Wow, that's horrible. Okay. We have these tuples, right? Entity, attribute, value. So in this case, what it would actually look like is something like entity 4 has an attribute named name, and the value is, SKSE. Along with that is also a transaction ID, which is like when that datum was inserted into the database. That tuple is often called a datum, like datum. And this model follows a lot the database model of Datomic. And then we have other metadata information, like if it's indexed, if it's optional, that sort of thing. So on the model definition here, if we say is optional, like we don't have to give a description, but with these others, you have to. But we also have a reference attribute here. So in this example model, we have load after, which is the value of this tuple, of the load after tuple, is a pointer to another entity. The cool thing about that is that, so like we have mods that can point to files. And if we go to the file, we see that the file has a reference to a mod. So these references kind of go backwards. You have a file points to the mod that it's in, and a mod points to the loadout that it's in. And it's like, well then, what if I want to go the other way? Well, because of the way we index these tuples, there's entity, attribute, value. We put those in a sorted set in the database and like on disk in multiple different configurations. And references also get indexed kind of backwards of value, attribute, entity. And that allows us to do these back references. So you see here, mod has a back reference to files, which doesn't actually mean it has an attribute. Mods don't have an attribute that points to the file. The file points to the mod, and then this says, oh, but you can also navigate that path backwards to get to the file. So these tuples are literally just like a tuple you would see in any other database or any other system, a struct of values, right? And then we index them in several different ways. So the main index types are txlog, which is essentially just the transaction ID comes first, in this case, the transaction ID in this system is a monotomically increasing U-long. So it starts at like 0, and then the first transaction, or it starts at 1, and the first transaction has ID of 1. The next one has 2, 3, 4, 5, 6, so forth. They go forward in time. So the TX log is sorted first by the transaction ID, and then the entity, and then the attribute, and then the value. All the rest of these are sorted in the way you would think based upon the name. So the EAVT is entity, attribute, value, time. Attribute, entity, value, time for this one. If it's a back reference, we index the value first, and then so forth. And then the is indexed marker, if we put that on the attribute, then it ends up in this index as well. And what that allows us to do then is, let's see our tests here. I'm looking for, we have a way to look up entities by the value. So we do find by name. So like we do mod.find by name because name itself is indexed. We can look in the index that is sorted by attribute, which would be name, and then by the value that we're looking for. And then that would give us a segment of the index that is sorted by all the entity IDs and time for which those are true. Now the history portion of this comes into play with this index type. So we have two EAVT indexes. One that's current, one that's history. Mods can have the same name. So all indexes are sorted by those attributes, and they are unique, but they're unique in the sense that none of those components will all completely match. So it is sorted by E, A, value, and then time. And because if you insert the same value multiple times, you would have a different T value each time. They're not, collapsed. It is a set, but they're unique enough. One of the things I want to add too soon is like a constraint that is, making sure something truly is unique, but we haven't added that yet. So what happens, so like you're just accruing this information, right? Every time you add data, you add in another tuple. So what happens when you remove it? So when you insert a new tuple into the database, you can say if it's an assert or a retract. Most of the time it's an assert, but a retract says, I have this tuple deleted out of the database. When you do, it pulls it out of the current index and puts it into the history index. And this is mostly an optimization method. Whenever you want to know what's currently in the database, you go to the current. What's kind of cool is that because they are moved from the current index into the history index, you could do something like this, which is an as of query. So it's pretty interesting to see what it's doing here. You give it a slice of the index that you want. And first thing we do is we go both to the current and the history and get the segments of the indexes that match your query. And then we concatenate those together, or merge them technically. We merge them together, and it's a sorted merge because they're all pre-sorted by the same sort method. So we can merge them. And then we can do a filter as of a specific T value. So every time you do a transaction, you get an incrementing TX number. That merged index can be filtered. We filter everything after that. So now we only have the datums before. And then within that segment, we can go through and find the datums that were retracted and not give those to the user. And this gives us time travel. So you can actually sit down at the database and say, show me the database as of transaction 1, 2, 3, 4, 5, 6, and walk through the database or backwards or whatever. And this is kind of what Datomic developed, and it's pretty cool stuff. We currently just do a really thin layer on top of RocksDB. Each one of these indexes are a column family in the database, essentially a different table in RocksDB. Something I'm thinking about doing later on is moving to a different model where we can store this, like segments of this in memory instead of in RocksDB. We can like load chunks of this into memory and access them directly as like as chunks of data instead of like spooling it in and doing work with it and spooling something else in out of Rocks. But we'll see if we get to that. And so it's kind of weird because one of the ways you deal with this, so the question is this used for like assessing previous versions of the loadout? Yeah, it is. And RocksDB has the ability to snapshot something as well, snapshot the database. Essentially, it's free because RocksDB itself is immutable. It gathers information, and then every once in a while merges all the new data with all the old data and deletes any files that are no longer in use. So when you create a snapshot in RocksDB, you can tell it, don't delete these files until I'm done with them. And that's what we leverage. So when we're doing work on this, like we're working with the database here, let me pull it up. It's in our tests. This is the kind of the pattern you do is that you insert some data and then you go to connection.db. This is free, and actually the DB value is always there, but it's a snapshot. So anytime we talk to this database value here, it cannot change underneath us. Every query we execute will be on the same version of that data. And if we ever want to get a new version of the data, we have to go back and do connection.db again. If it's updated, it may not have. And so this really is kind of like what the queries look like. You know, this is kind of a dumb query, but we're finding all the mods and then finding ones with a specific name and then returning those. We could just do this find by name, and that would work as well. But we did build source generators on top of this too, so that we can do like this. So we insert a file, 3 different files, and then once those are in the database, we can get them back out, and they act like a normal struct that you can read and write data from. And so, yeah, it is used for like different versions of the database, but it's also just a really nice pattern to deal with. Because the other thing is the way you build up these transactions, and let's look at this insert example data. What you're telling the backend is like, I just have new datums that I want to have show up in the indexes. It's not that's it. That's all you can really tell it. I want this data added. I want this removed. So we do have this little like DSL around it. Like I'm going to create a new loadout with this name, but all that's doing underneath is just inserting a datum with that value. So you create all your different entities and wire them up, and then you do commit. And what this commit does is package up all those lists of datums and send it to the back end of the database, which is a single thread that just processes those transactions one at a time. This is put into a queue, and then the back end processes that transaction, writes it to disk and all that. And then when this await returns, you know that your data is on disk and persisted and good to go. If we then call at this point connection.db to dereference the DB, it will have the data that we put in on this transaction. So we are limited to one writer to the database. That gives us our consistency. We are limited to one writer, but with one writer right now, depending what you're inserting, I've hit upwards of 500,000 tuples a second using one writer. So it's pretty fast. But because those transactions are just a list of things that you want to insert into the database, you can drive the whole app off of that too. And so we have this thing called observe. Observe datums. So for here, for example, we say loadout, observe all. And then we do this transform where we get all the names and we bind that to this list. So what this is saying is any change to anything that is a loadout in the database, let me know. So we can make this sort of reactive pipelines built on top of this. And that works out really nice for the app as well. Yeah, reactive UI is pretty cool stuff. There's some things I would like to do eventually with this, like we don't really have a query language built out for this yet. When you build complex queries, you kind of start at one place and then hop through the indexes to move through the database. And we don't have a live version of that yet. I would like to, but we'll build that out at some point. So what I'd like to be able to do is have a link type thing where you can build your query and then either say execute once or give me a live query where what it spits out is a reactive observable of like live objects that just change as things change. So, and actually, real quick too, these are like examples here. What's a good example here? So this is what we get out of the database. We have the entity ID, in this case, the attribute. So attributes are actually not stored as strings, they're stored as a ushort. So this index here we can see is the AVET current index. So it'll be sorted first by attribute, then value, then entity, then time. And we see that here. We start with 5 and it goes down to 3. I wonder why that's kind of a reverse sorting. It doesn't really matter. It's just weird that it's listed that way. So it's attribute, value, and you can see here, so dead beef 1 is first, and then 0, so forth, and then by entity. Yeah, this whole thing is sorted backwards. It's a little weird. But we see these 3 lines are all exactly the same, but then they're sorted by the entity last of all. And all of these were put in the same transaction, which is transaction 3. So what I did want to build today, one of the things I wanted to build is an excision routine. So I mentioned when things die, they get moved into the history index. But there is times like when deleting loadouts, when we really just want to flush it all out. We want to delete everything with the loadout, not just move it to the history. Like there are times where we want to be able to have an undo for deleting a loadout, but there are some cases as well where the data is a cache, or an image updated that we downloaded and we don't need it anymore. We can delete the old one, and we don't want that history sitting around. So this is normally called excision, and I think that's what we're going to build today. So the interface for this is going to go into the iConnection. And let me set my view. This is really big. Put this at 150. There we go. So the interface for this is just going to be an async method that we will give it a IEnumerable of entity IDs. So this will be a list of entities that we want to just completely flush out of the database. So I don't know. I spell it's been permanently wrong. Not excises. It deletes the entities with the given IDs. Also deleting them from any historical indexes. No, it's not. Historical really misspelled here? It is. Great. Okay. And I think we will have this return a ulong of returns the total number of datums that were excised. So what we're going to do with this is we will first query we'll first retract all of these. Oh, the autocomplete on the comments is GitHub Copilot. I actually am a huge fan of the AI stuff. I mean, it's like not flawless, but it's like the more typing and stuff you get in, the more it just really locks in and does the right thing. So we have kind of two layers to work this through. One's the connection and one is the backing, like datum store. So we'll put a inherent doc on this. So what we're going to do first of all is retract all datums for the given entity IDs. So we'll get the database. So the datums we want to remove are the I think if we want to do this in link, or I think we will do this in link. List datum to remove. Actually, these are retract, to retract. So we're going to first move them all into the historical index so that everybody who's watching for any changes sees the changes in the update system through those feeds of like database changes. And then once we're done, we're going to go through and delete them all, everything from the historical indexes for these. So for each entity and entity IDs, we're going to get the datums for this entity. And what we get is index segment, and then we're just going to do to retract. So we're getting the portion of the EAVT index with these, and then we'll add those into our list of things to retract. And then we just need to create a new transaction. For each datum in that. And I think I have an override that allows us to retract. I do. That just converts it to a retract datum. So we do tx.add. So we're adding this datum.retract takes the datum and turns it into a retract datum. That just sets the flag as being retractable. And then we add that to the transaction. And then when we're done, we await the commit of that. So now all of those have been moved into the historical index. Now delete all the datums from all indexes. And I think we have to do this in the backing store. So we do excise, and instead of entity IDs, well, first we need to get all of the list datum. So we'll clear out the old to retract.clear. Yeah, we'll name this datums to remove. So they're all in the historical index, but there could have been other datums in the historical index we need to also now pull out. So we got to query all of the historical, all the different indexes where these datums could be in, which at this point will be only historical and the transaction log. And then we need to delete those. But actually, all datums are put in the EAVT and AVET indexes. So we can look up just the datums we need from the EAVT historical index. Yeah. And then we can hand that to the back end and say, just try to delete these datums from everything, from all the indexes. So let's do that. So this datums method here goes to the store and gets a chunk of the database datums. But it has a couple other overloads that can let us look up stuff by entity, attribute value, so on and forth. What we're doing here is a little more controlled. So we're going to do a new slice descriptor, which is like a description of the start and end of the index slice we want. And this is a slice descriptor of, I think we need create, not new, index type, and this is going to be the EAVT history index. And we want the entity ID. I don't know that we have an override for this yet. No, we don't. So we'll create one. Range. Index type must be either EAVT current or history. Yep. Cool. Delete a little too much there. Okay, so we're going to return a new slice descriptor. And index type. So this is what I do like about the Copilot thing, is that like it read the doc string, and all I typed if index type is and waited, and it filled out the rest of this because it read the doc and realized there's a constraint on what the index type can be, and it wrote that code and detected that. So the datum is set of NTID EID here. So we want to go from EID to EID, and the attribute ID is either min or max, and the rest of this is just min or max, right? So this will get all of the datums in that range, and then we add those here. Have this take an array just because we don't want to do multiple enumeration over that. Okay, so now that we have a list of now we have a list of the datums we want to actually go and delete. And so we can do store delete, we'll call it excise. And this variant of it, we don't need to look anything up. We actually just have a list of all the datums to excise. And this one can actually be internal. Internal deletes these datums from any of the indexes. They are. Have this return to ulong. Well, I don't know if we do want a ulong there. I don't know if that's ever going to be useful to actually return the number of things we deleted. Okay. Oh, it's internal to the specific namespace. Oh yeah, this is an abstractions, isn't it? Okay, that's fine. But we can here return the datums to remove.count. That would work. Okay, so now we'll have to go to the datum store. So the datum store's job is it just maintains the indexes. You shove datums at it, and it maintains them. So first thing we need to do is we need to create a batch. And then for each datum. So one of the things that's kind of interesting about how I've set this system up is that, as I mentioned, datums are stored in different column families in RocksDB, and the only difference between those column families is the sort comparator. So the data in each index is exactly the same datums. It's just when they're input into that sorted set in RocksDB, they are sorted in a different order, which is pretty cool. It means we won't have to change any of this data to get it to delete. So we'll just do this. All 4 or 5 indexes, and then txlog.delete. And then batch.quit. That actually should be all it takes. And this doesn't even have to be async, although we could leave it that way. Maybe when it's a value task, we can do that. So the difference between a batch and a transaction here is there's kind of 3 levels to this database. We have the backend, which is either RocksDB. Currently, it's either RocksDB or an in-memory sorted set, like an immutable hash set. On top of that sits the datum store, and the datum store is responsible for maintaining the indexes. So it looks at the datums and says, oh, this is an index datum, so it needs to go here. This is a something, it's a reference datum, so it needs to go in this index, and that sort of thing. The third layer is the connection itself. That's kind of the user-facing thing. So the user gives the connection a list of datums to process, and the connection mostly just hands that to the datum store, which then turns those into like storage level operations. Like it needs to go into this index, into this one. We need to move it from current to history, that sort of thing. Because moving those datums too is not, moving them from current to history is not the responsibility of the user. The user can just say, here's the new name for this mod, and the datum store will look up the old name, issue a retract for the old name, and then issue an assert for the new one. So that middle side just kind of coordinates those. So this batch is kind of a storage level transaction. We need to make all these changes to all these different indexes, and we're going to batch them up together and do it now as one thing. And we can actually see here, so datum store has this method called log. Where is that at? Finished. Here we go. So this is the guts of it. This is that single threaded queue that just goes through each datum in the transaction here and figures out what it needs to do. Because another thing that needs to happen in the datum store, and I didn't mention this, so we have that entity ID, right? The entity ID is also increasing over time, and it needs to be unique. It's a 64-bit ulong, so you don't want 2 entities clobbering each other. So when the users are creating transactions, they create them in whatever threads they want, and then create those transactions that they hand to that one thread for it to execute. So the question becomes, if you make entity 2 and I make entity 2, what do we do, right? So in the system, there's this thing called partitions. Those entity IDs have a partition. It's the top byte of the ulong, and it can be multiple different things. So the first partition is the attributes. The attributes themselves are entities with metadata on them, and they exist in the first partition. The second partition is transactions. Transactions are entities. So every time we have entity attribute value transaction, that transaction is actually a reference to an entity that has metadata about when the transaction happened. So you can actually query the transactions and attach extra data to them, and audit trails or whatever you wanted. And then you have the entity partition. So when two people are creating their own transactions, or two threads are creating their own transactions in parallel, they create them in the temporary partition. And then that datum store, when it's digesting the transaction, says if a given entity ID is in the temp partition, then that's just a temporary value. One does not mean one there. It means within the context of this transaction, it's 1 or 2 or 3. So the datum store takes those and translates those into an actual database value that is known to be unique. And that assignment has to happen in that single thread so that we don't get any clobbering of the different IDs. And then there's also user partitions, which we won't worry about. These are like users can put their data in other partitions to segment it on disk so that it works better with caches. So that's one of the key things that happens here in this datum store is you hear, like we go through the datums and we say, is it in the temp partition? If so, we need to remap it. And we remap the E value to a different E value. And it has to keep track of the IDs it assigns, because if the same ID is used multiple places in one single transaction, it needs to remap those all to the same value so it all links up the way the user expects. Okay, so connection. Oh yeah, we were in that, let's see, we were here.
Players control a ship, which begins each mission positioned at home base.
Excise.
From there, players can fly to 5 planets, avoiding...
Oh, that's right, we changed this to an entity ID array.
There's the standard upright cabinet with colorful side panel graphics. A new streamlined cab array, contemporary and compact. And the wood grain...
Well, I feel like this should work.
Ideal for comfortable gameplay in relaxed locations.
We just need to write a test for it. So let's do that. Yeah, it's interesting. If you want to learn more about a lot of this, feel free to look up Datomic, the database Datomic. There's a bunch of tutorials about it online, and just like seminars and stuff about it too. But this is kind of the guts of Datomic with all of the distributed nature of it removed. So Datomic ends up being a lot more complex in a lot of cases, because what they have in that system is you have one machine doing all the writing, and then everybody ships their transactions to that machine. But they can read concurrently. Everybody has read access, and so you can scale reads out to hundreds of machines, and they just send their updates through that one machine. There's a lot more complexity that is involved in that we don't have to deal with here. We can do a lot of stuff simpler because we don't have to deal with the network stuff. So can excise entities. So what we're going to do is we're going to insert two. What I want to do is I want to insert two loadouts, change the name of one of them, make sure the history of the loadout is there, and then excise it, and we shouldn't be able to see any of it. So let's do that. But the old loadout should be there still. So L1 equals new loadout new. We'll create a transaction. TX. So we have test loadout 1 and var L2. test loadout 2, and then we will commit this. And what we get out of the commit is a commit result. Because what we have here are new loadouts. These are loadouts that haven't been inserted yet into the database. Yeah. It's Clojure was the powered a lot of Datomic. So I had mentioned this yesterday. There's other databases like this. So one of the problems you run into in Datomic in like bank situations at times is that I mentioned like the transaction ID is always increasing, but that's the transaction ID that the server sees. And so that's called, it's a temporal database. MnemonicDB, what we're writing here, is also a temporal database. But XTDB, written by a company named Juxt in England, extended that whole idea into multi-temporal data, where you can have 2 views of time, which is kind of crazy. You're like, why would you want that? Well, there's when the bank processed the check and when the server saw the check that you sent in. Those are 2 different things. And so sometimes we have to, that's what they were concerned about, is that like, if you ingested a whole ton of data that were from backups or something, the server would have seen the time at when you imported it, which may not have been the time the data was created. So Juxt has that one. There's a couple others that like run in the browser and stuff, but this database concept has been cloned several times now. Okay, so we get the commit result. Now we need to actually get our loadout read only 1 and loadout read only 2. So that's what these remaps do. Is these were temporary IDs. They're now mapped. And that's type checks, so like you can't actually screw this up, it just won't compile. Okay, so now what we want to do is we want to modify loadout 1, var L2, var tx2. So we're going to begin a transaction, and then we're going to we are going to do a tx2.add. So we're just going to do add on L2, and say we want to change the loadout name to test loadout 2 updated, and then we're going to commit that. And then L2 read only dot rebase. So the rebase just says, hey, we've done something, we want to reload that entity. So now this will have the updated, and we can check for that. So L2ro dot name should be updated, and we can test this to make sure it all works correctly. We should also do the L1 read only name should be test 1. Oh, we're using the wrong ID there. We didn't use the remapped ID. That's what the problem was. Okay, cool. So that works. We get the 2 loadouts. Now we can also show the history. Yeah, no need to manually look up ID. Should it be before the rebase? Well, I'm not sure what you mean by that. Oh yeah, I would have expected the name to change after rebasing it, correct. The problem was that I had used L2s, like the ID here. This is all like immutable data, so it was using a temporary ID and making yet another copy of it, like an actual separate entity, which was the problem there. So here we are updating it, and that's good. Now, it is possible to get I'm trying to think of the best way to get the history of this. We also don't have the ability yet in this system to get the history. like what I want to do is get a history database. We could code that up. I'm wondering if we code that up now or we... Yeah, let's code that up now. Because that'll really help for testing with this. So we have as of here. So as of on iConnection is literally as simple as give me a database as of this transaction ID. So what we're also going to do is IDB and say history. Returns a IDB or a snapshot of the database that contains all current and historical datums. So it's still an IDB. You can query it the same way you want. You can, everything you need to do there. But it'll contain everything. So we'll be able to see both of those changes if we do this right. So we go into connection. I needed this for something else anyway, so might as well code it up now. Do as of. So what we also have here is we have these snapshots, and a snapshot just has two methods. You give it a slice descriptor, it gives you that index. So we really just need to build another snapshot and expose that here, which we'll do. So public IDB history. We can inherit that doc. I don't know why I didn't do that. And then here in our, we have as of snapshots here somewhere, right? Yeah, so we'll do add history snapshot. So the iSnapshot here is the internal storage's snapshot. And then we need this attribute cache in some cases. And so I think what we'll do is we'll just copy all of this and delete the parts we don't need, because it's basically this code minus a few things. And history snapshot. We don't need the TXID. We will need a TXID though, I guess, for the maximum database value. But what we're going to do is we get the two datums and we build the merged segment, but we do not filter it. I guess we could filter it as of a specific time. I don't think we need that though. We don't need filter, and we don't need to apply the retract. So the apply retract is kind of where we would remove all of the retracted datums. But in this case, we want all of them. And we feed those into the index, and that's it. So same sort of thing here. We get the two types. We don't need merged or filtered. Or we do need merged, but not with retracts. The two interfaces we have here are a chunked version that gives you chunks of indexes. If you're going to load a gigabyte of data or something, you may not want to load it all too fast or in one chunk. And we don't need these methods. And because that's not needed, this is not needed. Boom. So now we have our history snapshot, and we can go back to the connection and do return new DB. So really what we're saying here is, the database has all these ways of querying data and caching it and that sort of thing. The DB object does, but the snapshot actually handles loading data from the index. And so we're just giving it different ways, we're basically injecting different methodologies into how to load the indexes. Here we merge the two indexes and filter out anything we don't want. In the case of history, we just merge it and everything's included. So now we go down to our test again. And what we should see is bar history, connection.history. So we get the history database. And now if we query all the datums for this entity, so L2 are history equals history datums L2RO.id. We are going to, if we pause here and debug this, what we'll see is we should see both of these datums in here and a couple retractions too, and we can make sure that that is the case. So this history, so we see in our results is this is sorted by TX. We first inserted a value. Well, we don't have a way to render the value, unfortunately, with this because it's not resolved, but we can resolve it here. So datums L2RO ID, and then we got resolved. I need to work on how that's printed out a little bit. Well, we can see here, we had a datum inserted with loadout 2 in transaction 3. In transaction 4, we removed it. And in transaction 4, we added the new value. So the history works, which is cool. So what I think we'll do is if we resolve all these, so we're going to get the datums, we're going to resolve them, and then we're going to say, so the low-level datums have this really primitive view of what the values are. In this case, the values are UTF-8 strings, but like there's not a lot of way of like viewing those and verifying them. So resolving them converts them into UTF-8 strings, which does allocate data, but it's easier for testing. So then if we do where the datum.is retract equals false, so we don't want the retracts, we just want the asserts. And then, actually, you know what we'll do instead? Select. We'll do of type first, loadout.name. We'll get the datums that are strings, and then we'll just return retract value. Look at that. And actually, ChatGPT was able to just caught what the actual type of that everything is there. It's pretty cool. I love that. Okay, so this passes, and we see that it's a... I'm going to invert this around so that we do not retract, so that we can see true as assert and false as a retract, because otherwise it just gets confusing to have double negatives in the code. Cool. So we verified the histories there. Now what we're going to do is we're going to try excising this data. And so connection excise, and we're just going to excise R2, L2RO. Now, if we get a new history database, and we do this, we should have nothing in here. No names dot should be empty. But the other one should not be empty, because we shouldn't have deleted the wrong. Okay, cool. So we get an error. So it says should be empty, but we in fact found values. So apparently I didn't do at all what I thought, which is not entirely surprising. So if we go to the X size, let's step in here and make sure that we're actually getting the data we think. So datums to remove, we have one entity. We're getting the segment. So we do need to okay, so we get the one that we need to retract. Retract that. What's interesting here, though, is that we are still querying the same context database, not the one after this transaction. This is something that gets kind of tricky in this system, is that you do have to remember to, whenever you make a change, update whatever database you're looking at, the value to the new value. So context DB should be the new database. And then I think this should work. Nope, it did not. Okay. So we have one datum to remove there. So this didn't actually find anything to delete out of EAVT history for some reason. That's interesting. Let's maybe look at that again. First of all, I want to make sure that the entity ID that we get here is in the correct partition. I believe it is. 2, yeah. So when we go into here, oh, yeah, we didn't actually use the right index. It didn't pass that on to the backend. Still not quite there. So we are seeing 4 datums to delete, which does make sense because we have the initial assert, the retract for that one, the second assert, and then the retract that we've added to the backend, right? So now our datums to remove includes 4 datums. And when we go in here, into X size, that's interesting. We are properly writing this data to be deleted. Oh, you know, part of the issue is here is we aren't like nothing's actually creating a new database. A new, you know, like we're going to the back end and deleting the data, but that doesn't actually update anything in the front end. So I do think that in the datum store, or the connection here, once we're done with this excise, we should probably... So Datomic does this. It like... You can forget something, but you have to remember that you forgot it. Yeah, absolutely. Thanks for stopping by. So excise was originally included in Datomic as a GDPR compliance thing. That it's great to make a database that can never forget, and there's really not technical issues with that. But there's times when people have the right to be forgotten, and so to comply with laws, you got to add something like that. But there's a difference between just straight up forgetting something and remembering that on this date I forgot something. Actually, not against doing that here. So we do have transaction attributes, and I forget where I put those. And built-in entities. So we can do public, static, read-only, and this could be a ulong. Do we not have a ulong attribute in here? No. We can make it a uint attribute. Well, so when we define a new low-level type of an attribute, this is what we do. So this is a ulong mapped to a database ulong, and every attribute needs a namespace and name. So we pass that in with the database tag type, which in this case is ulong 64. Then we just implement a couple members here, return value. It's always getting this wrong. Oh, we don't need to doc string on that. Okay. So we'll just have an optional oh yes, I based this off the wrong thing here. Scalar attribute. There we go. Okay, so if this database is associated with a so after this, what we can do is create another transaction, add. Now the ID here is txid dot changes of an entity over time. Cool. We will commit this, and then this PR will be done. That's about what I have for today. Bit of a shorter stream today. I like to try to find some things where I kind of know what I'm doing and I'm not just sitting there staring at a screen, pondering where I went wrong. So, yeah, thanks everyone for coming and watching, and hope to do a bit more tomorrow. We'll see. Around the same time. I'd like to get a schedule going a bit more too, but fun times. Thanks again, everyone.